I guess we get it on. So also very welcome from my side. I'm Franz Sperl, working in the product management at the company Günther, and here now on behalf of Euromon to present a little bit about ammonia, the direct expansion mode and pump mode, and something what is happening in between of it, which is quite interesting, and I will show you a few things. All in all, also just for the background, I'm working also in Euromon in the technical committees, heat pump, energy efficiency, and secondary loop. So something is always going on there, and all are happy to. It would always be good to have more to join there. So for the agenda, I start with a little introduction and the motivation behind that. Show you the test chamber, some measurement campaigns that we did in our laboratory, and show you the results and give a conclusion. All in all, we start with normal standard, let's say, at the moment, industrial standard products for ammonia pumped. Usually it's an evaporator with horizontal header going straight through and upward start. And of course, could be also a vertical header, doesn't matter. All in all, they are working pretty fine, are robust and great against any load fluctuations. And we do see here now a graph that shows the specific refrigeration capacity plotted against the recirculation rate, which is on the x-axis. And you see that for the recirculation rate, it depends on what capacity comes out of the evaporator, depending on which recirculation rate you adjust for the evaporator. And depending on the circuiting, you either have a stable plateau for high recirculation rates or for a little bit lower recirculation rates, but usually there's a little bit of drop-off when it comes to smaller recirculation rates, which is at the moment a little bit the aim to reduce the total ammonia charge in the system, and therefore it is one possibility to reduce recirculation rate, but it is not really possible for all evaporator because they are not applicable for it. And so it's sometimes also interesting if it comes to system optimization, it shouldn't be done in existing systems, just replacing or putting in a gas quality sensor, reducing the recirculation rate, then it might end up in a capacity lag. But there is something to do against that, especially then for new systems, of course, it's easier. Just one thing, of course, recirculation rate is something to reduce, but also direct expansion is a possibility. And just to sum up or give a little bit overview, you all might know what is the difference between direct expansion and overfeed mode. To start with the direct expansion, you see the H-log P diagram. And all in all, the important thing is that the liquid refrigerant enters the evaporator with a certain gas quality at the beginning and comes out of the evaporator with a certain superheat ratio. In comparison to that, in pump mode, you enter the evaporator completely liquid at the inlet and coming out with a certain gas quality at the outlet, which is a mixture between gas and liquid. And now the aim is to compare those two operation modes and see what's happening in between also. So here's a little bit of an overview between also those two operation modes. On the right side with the pumped, we see, let's say, the standard industrial evaporator. Recirculation rate is defined by the enthalpy difference at evaporation temperature of the two-phase area by the evaporation the enthalpy difference within the evaporator. And so when going lower in the pump mode, you get somewhere close to 1.0, where everything you pump into the evaporator will liquid one will evaporate, and then it starts the superheated area But for the superheated area, you usually talk about superheat and superheat ratios, and usually for evaporators that are applicable for that system, which is one with Venturi distributor, capillaries distribute the liquid evenly to the circuits. And some theory behind that is also that you can find in literature, of course, if you have a lower superheat, usually capacity rises, and until you get a maximum, and then it drops off again. And we see what it turns out in the results of the tests. So maybe the best result might be at 1.0, but we will see. The tests that we did are in our laboratory in Fürstenfeldbruck. You see the machinery room, the rack in front with a compressor, a screw compressor in this case, and in the back here is the liquid separator, the vessel, and now we just jump through the door and we arrive in the test chamber. You have the evaporator placed in the middle in a metal frame, connected to the ammonia side, and those air coolers beyond the ceiling, they are there to keep the temperature in the room constant, either with warm glycol or with electrical, depending on. So we just jump quickly to the measurement campaigns. All in all, it bases on the DIN EN 328, all measurements. It's just, look at this H-log-P diagram. The graphical illustration is more easy to remember about. It's just that you have a liquid temperature and a gas quality at the inlet and certain superheat ratios at the outlet. Superheat ratio is defined by the superheat divided by the inlet temperature difference, which means evaporation temperature to air inlet temperature. And for a superheat ratio of 0.65, it means a superheat of 5 Kelvin at 8 Kelvin delta T1. So far, so good. First campaign, certain superheat ratios. Second campaign, we see what is happening when we have different subcooling temperatures. What's the impact on the capacity of the evaporator? And then the last part, we keep the liquid temperature constant at around about evaporation temperature, which is then completely liquid and the same situation as it is for pumped operation mode. And then we could compare it for the pump mode, which will be the first part of the next campaign, to see if we can really compare those two operation modes and everything is consistent. Then we have the same conditions on the evaporator, either with high liquid expanded into the evaporator or with low pressure liquid pumped into the evaporator. And in the last part, we will then focus on the real recirculated overfeed mode of the evaporator and see what is happening there. So we just jump to the results. We have the first part. To start with, it's an optimized evaporator for this new kind of application. And you see kind of the direct expansion design of an evaporator. And you will always have on the right side the illustration in the H-log-P diagram, what is happening in the evaporator at this condition that we are testing. And now I'll show you the diagram, superheat capacity diagram. So we have the superheat ratio at the x-axis and the specific refrigeration capacity on the y-axis. And what we can see here, or just to understand also, superheat ratio means with a higher value of superheat ratio, it's also a high superheat. And with a lower superheat ratio, it's a low superheat, or at 0, it's non-superheated anymore. So if we have high superheat ratios, the capacity kind of drops off because a lot of surface is used for superheating. But what we can see is that after a certain point of 0.8, which means around about these 7 Kelvin roundabout at delta T18, it's a quite stable plateau, and the capacity does not rise really a lot. So all in all, doesn't matter if you have 7, 5, 3, 2 Kelvin of superheat, you do not get really a lot of capacity more out of the evaporator. It's just more complex to control it. And further on, we did observe that below a superheat ratio of 0.6, you also have droplets flowing out of the evaporator in the gas flow. So that's one thing about direct expansion. We will have a look what's happening with subcooling. So usually you have a higher enthalpy difference, you think you get more capacity out of the evaporator. But what you can see here, when plotting the subcooling or liquid inlet temperature into the evaporator to the specific refrigeration capacity, it is also quite stable. But at the end, it drops a little bit, almost 10%, even as the enthalpy difference is maximum. And what's the reason behind that, when we have a look at the mass flow that gets into the evaporator, and to get the same superheat at the outlet, you see that it's a constant drop-off in the mass flow, because the direct expansion valve will all in all close more. And at the state where you have completely liquid at the inlet, the state at the inlet of the evaporator is different. You have completely liquid, you have less turbulences. It's a little bit a different situation there, and you get less capacity out of the evaporator if the subcooling is too high even. And you see a drop of 20% in the mass flow. Now we look at this third campaign, which is kind of the transition also already, or the one part, still direct expansion mode, but the situation of the evaporator is like pump mode, but with superheated outlet. And you get also the curve, which is quite similar to the direct expansion one. And I simply plot over also the first part of campaign number 4, which is then the direct comparison, normal direct expansion mode with high pressure liquid, and pump mode with low pressure liquid pumped into it with the same superheat ratios adjusted. We see it fits very well. So that's kind of a proof of concept that at least we can compare the operation modes, direct expansion and pumped. It's somehow consistent and works out. And now we can move on and see how does it really react compared to the normal direct expansion mode with a certain gas quality at the inlet. And there we see a difference of 7% in capacity, that some gas at the inlet of the evaporator is positive for the capacity. And now I simply move on to the next slide, where we have the second part of pumped. So now we have just look what is happening in the direct expansion, and if we can really move on with the pumped. And here we have now modified the graph that you have on the x-axis, the recirculation rate now, and the specific capacity on the y-axis. It's a similar graph, but of course with a different x-axis. All in all, you could imagine 0.1 is when it's completely gaseous, so on the left side of 0.1 would be superheated. And we see that there's a steep increase once more liquid enters into the evaporator. All surface within the tubes, they get wetted and take part in the heat transfer and evaporation process, and therefore we gain in capacity. The maximum here we see at the recirculation rate of 1.2. So 20% more liquid going into the evaporator than needed all in all for evaporation. And afterwards, it constantly drops off. So we see that if in a usual concept with a recirculation rate around about 3, compare it to a 1.2, the mass flow can be reduced by 50%, and we see a reduction of pressure drop of 40%. And of course, the pressure drop directly influences the logarithmical temperature differences for the evaporator, and therefore you have this capacity difference. And as I already mentioned, 1.0 is kind of the division between recirculation rate and now the superheated area, and I just kind of divide the x-axis in a recirculated part and a more commonly superheat ratio part. So that is a little bit divided, but it can be done that way. As superheat 0 for the left side is the same as pump ratio 1. And if we have part 1 and part 2 combined, you can see the recirculated part, and there's the transition to the kind of superheat area. Both are pumped mode, but either superheated or outlet, gaseous and liquid. And even here, the mass flow is much lower, and of course also the pressure drop. And the capacity difference is around about 30%. But if I plot in now the normal direct expansion mode with some kind of gas quality at the inlet, which is number 1, the usual direct expansion mode, we see a capacity difference of around about 20% between direct expansion and pumped with this optimized evaporator. Which already brings me to the first part of the conclusion. We remember this graph from the beginning where we have this standard evaporator with a pump ratio of 3, or recirculation rate of 3. The normal standard industrial style. It is quite established and it works since decades. It's a good product and works, and still is used a lot. And it's definitely really great for also high capacity fluctuations in systems. But there's this little lack of capacity in lower recirculation rates if that's necessary. So we jump to this optimized design where we see we can do with smaller core tubes in this case and a little bit of balanced pressure drop. We see that the tube volume will be reduced by 60%, and that results, of course, in a first reduction of ammonia charge, as there's just a smaller volume, and you can have less refrigerant in there. That's the first part. It is used as direct expansion mode. So what are benefits for direct expansion? Of course, it's the lowest charge possible. There's no need of a big separator in the machinery room to just separate all the liquid that would be coming out of the evaporator in a pump mode. And one nice thing also, for example, for cold storages and installations where there's a big height between the evaporator and the tubes or the suction line, within the risers, there's kind of a pain when there's a lot of liquid in there because it results in a lot of pressure drop. With direct expansion, that's a good idea to do that. On the other hand, for low recirculation rates, we see a maximum of capacity in 1.2, which is quite low value, and the capacity is higher compared to direct expansion by 20%. So also good here. But you could say, okay, whatever, how does it behave against or compared to the standard product? And I did just plot in the graph now for the new one, which is highlighted in blue, into the old illustration kind of for the recirculation rate. And we see that it is even a little bit higher capacity value than we do see for the standard product. So it is definitely competitive to the standard one, and it is, of course, efficient and cost effective, as you can use less surface for the same capacity, and therefore less investment costs. Less pumped liquid that needs to be circulated in the system, and also the separator could be smaller than. So far, so good. That's my part for this time. I'm sorry it was a quite fast running through and a lot of info that was around, but it was not easy to shorten it even more. So if there are some questions left over, happy to answer. Thank you. Haben wir ein Mikrofon? Ah, okay. I repeat. So how many degrees of superheat for a normal operating expansion valve? So all in all, for ammonia, usually it is a little bit more, like 7 Kelvin. But with the electronical expansion valve, we did operate it down to 5 and 4 Kelvin. And below that, the gas quality sensor makes sense. Yep. So to sum that, all in all, it was based on the standard conditions. Yeah. So it was the question about the temperature differences and the absolute evaporation temperature. So the standard condition is at evaporation temperature of 8 degree or minus 8 degree Celsius, 0 degree air temperature, which means a temperature difference of 8 Kelvin. And superheat, depending on the superheat ratio, 5 Kelvin for the 065. And there, then of course, going lower for lower superheat ratios, down to 4 or 3 Kelvin, and going up to almost 8 Kelvin. But of course, once the superheat gets very close to the temperature difference, there's not a lot of capacity getting out there. That was the steep drop down in the curve. No, evaporation minus 8 degrees C. I don't remember the value in Fahrenheit, sorry. But 0 degree freezing point for air temperature, and then 8 Kelvin below. All in all, the reaction of evaporator is quite similar. So you will also have this graph, which is quite stable for a wide range of operation, and then it will drop off once you get close to the super or air inlet temperature. But how it is angled and on which niveau it will be depends on the system design and the circuiting. So it will be different, but in the same way. Right.
Thank you, Franz.
Thanks.
For you. Thank you.
Nice.